Students, good morning. And now we are coming to our next topic, crystal defects. Most important topic, students. While we're discussing about crystal defects, first of all, how defects are arises in the crystal, it's a very important thing. Students, are you remember third law of thermodynamics? The entropy of a pure and perfect solid substance is zero at absolute zero temperature. That is a statement. Means, students, at 0 Kelvin temperature, every solid is a perfect crystalline solid. Perfect crystalline solid means, students, generally if you consider NaCl solid. Students, just imagine. I just represent a small crystal lattice arrangement for NaCl now. To well understood what is crystal defect. So, say this is Na plus. Say this is Cl minus. Say this is Na plus. Say this is Cl minus, once again Na plus, once again Cl minus. This is a perfect crystal, okay? No defects are there. But students, just imagine, once temperature increases, students, once temperature increases, then obviously some deviations are obtained in a perfectly ordered arrangement of crystals. Once temperature increases, obviously deviations result. Deviations means some of the ions are missing from their lattice positions. Just imagine, this is Cl minus, this is escape from the lattice position, or Na plus ion, this is escape from the lattice position. Okay, so we found some ions are missing from their respective lattice positions, which create the defect. Students, are recorded? Or this is simply called imperfection. Okay, so whenever temperature increases, students, keep in mind, every solid substance experience such defects. Okay, and that's why arrangemented structure becomes disordered structure because defects are there, and that's why the entropy of the system is also gradually increases because disorderness increases once temperature increases. Students, you know one thing, these defects may also be called thermodynamic defects. You know why? Because every crystal experiences such defects with the continuous increasing of temperature. So these defects depends upon temperature, and that's why these defects may also be called thermodynamic defects. Students, and these defects again classified into two types. The one is point defect and another one is line defect. Sir, what is point defect, sir? Point defect is nothing but it arises at a particular lattice position. So only here Cl minus ion is missing, or only here Na plus ion is missing. Only one lattice position. So కేవలం ఒక lattice positions లో మాత్రమే defect arise అయితే, and that defect what we call point defect. Students, if that defect arises along one line, okay, so along one line we found deviations along one line. Okay, so Cl minus ion missing here, Na plus ion missing here. So if we found defects along one line, and such defects what we call, students, line defects. But students, in this particular chapter, we are interested to discuss about only point defects. Okay, students, just look at how point defects are further classified. Point defects are further classified into three types: stoichiometric defects, non-stoichiometric defects, and the third one is impurity defects. Okay, so generally, students, in case of metallic crystals, మన సాధారణంగా మెటాలిక్ క్రిస్టల్స్ తీసుకుంటే గనక, అంటే ఎలిమెంట్స్ మాత్రమే ఉన్న క్రిస్టల్స్ తీసుకుంటే గనక, ఈ పాయింట్ డిఫెక్ట్స్ని మనం ఎలా డిఫైన్ చేయొచ్చు అంటే, అందులో ఫస్ట్ వన్ వేకెన్సీ డిఫెక్ట్. నేను చూడండి ఎంత క్లియర్గా నేను మెన్షన్ చేస్తాను వేకెన్సీ డిఫెక్ట్ని. ఫర్ ఎగ్జాంపుల్, నేను సోడియం మెటల్ తీసుకున్నాను అనుకుంటాను. ఇక్కడ స్టూడెంట్స్, సోడియం మెటల్ తీసుకుంటాను అనుకుంటాను. సోడియం మెటల్ అంటే ఈ ప్రతి లాటిస్ పొజిషన్స్లోనూ సోడియం మెటల్ ఉండాలి. Just look at sodium. Sir, what about here, sir? There is no sodium. That's what we call defect. Okay, now, so the atom which is actually present in the lattice position is missing to create a vacancy. Okay, and such defects which create a vacancy at a particular lattice positions we simply call vacancy defect. Okay, so due to this vacancy defect, we observe one thing: density of the crystal decreases. Students, density of the crystal decreases. Are you got it? Because some of the ions are missing, and obviously density is the crystal is decreases, because density is nothing but a ratio of mass by volume. Okay, volume is same, students, volume is same, there is no change in volume, but there is a change in mass because some of the ions are missing here. Mass decreases. Okay, obviously mass by volume decreases, and that's why density is gradually decreases due to vacancy defect. Sir, what is interstitial defect, sir? Very, very interesting one. Interstitial defects means, students, we just look at, now let us consider another metal. Let us consider another metal. Okay, students, just imagine this metal is M. This is M, this is M, this is M. Students, this is M, this is M, like this. And here there is no metal M. Where it is, sir? It is also missing. No, no, this is not at all missing. This is just shifting to interstitial position, like this, interstitial position. Okay, so whenever some of the atoms are enters into interstitial positions from lattice position, and such defect what we call interstitial defect. Okay, and due to this interstitial defect, there is no change in density. Just look at, there is no change in density. You know why? Because here atoms are not completely missing, they just shift their position from lattice point to interstitial point. This is what we call interstitial defect. So students, so now we are coming to the concept of point defects, and first of all we are discussing about stoichiometric defect. Okay students, now let us coming to stoichiometric defect. Sir, what is stoichiometric defect, sir? We just look at the definition going on here. Stoichiometric defect arises in such compounds in which the number of cations and anions are exactly in the ratio indicated by their chemical formula. Means in these stoichiometric defects, there is no disturbance, students, for stoichiometry of compound. Compound యొక్క స్టాయికియోమెట్రీకి ఎటువంటి డిస్టర్బెన్స్ రాదు. ఓకేనా, అంటే డిఫెక్ట్ రాకముందు క్యాటయాన్స్ యానియాన్స్ రేషియో ఎంత ఉందో, డిఫెక్ట్ వచ్చిన తర్వాత కూడా క్యాటయాన్స్ యానియాన్స్ రేషియో అంతే ఉంటుంది స్టూడెంట్స్. ఓకేనా, అటువంటి డిఫెక్ట్స్ని ఇచ్చేటువంటి కాంపౌండ్స్నే మనం ఏ డిఫెక్ట్స్ అని పిలుస్తామంటే స్టాయికోమెట్రిక్ డిఫెక్టెడ్ కాంపౌండ్స్ అని పిలుస్తాం. అర్థమవుతుందన్న. సో స్టాయికోమెట్రిక్ డిఫెక్ట్ కాంపౌండ్స్ నేను ఎక్స్ప్లెయిన్ చేసే ప్రయత్నంలో ఒకసారి నీకు నేను నాన్ స్టాయికోమెట్రిక్ కాంపౌండ్స్ని కూడా ఎక్స్ప్లెయిన్ చేయాలి. అసలు మరి నాన్ స్టాయికోమెట్రిక్ కాంపౌండ్స్ అంటే ఏంటి సార్? వెరీ వెరీ ఇంట్రెస్టింగ్ వన్ ఇది. స్టూడెంట్స్, మీకు గుర్తుందా టైప్స్ ఆఫ్ హైడ్రేట్స్? మనం ఫస్ట్ ఇయర్లో నేర్చుకున్నాం. అయానిక్ హైడ్రేట్స్, కోవలెంట్ హైడ్రేట్స్. I remember third type, non-stoichiometric hydrates. Students, means what, sir? Interstitial hydrates. Interstitial hydrates. Okay, now let me give an idea. Interstitial hydrates: zirconium hydrogen 1.92. This is a non-stoichiometric one. We are confused actually, sir. What is 1.92, sir? What is 1.92 here? Actual formula is ZrH2 kada. What about remaining 0.08s are here? Students, we know one thing. Just imagine this is zirconium. Just imagine this is zirconium. Students, this is zirconium. Okay, now hydrogen gas is sent into crystal lattice. So total hydrogen of course enters into actually lattice positions, but what happens? Some of the traces of hydrogen, very very small amount, it is entered into what positions, students? Interstitial positions, which create some defect. ఓకే, సో మనం పంపించింది కంప్లీట్గా 1 mole H2 అయితే మిస్సింగ్ ఎంత కనబడుతోంది మనకి? 0.08 మిస్సింగ్ కనబడుతోంది. ఓకేనా, అంటే మనం పంపించిన దానికి లోపల చేరిన దానికి స్టాయికోమెట్రీలో ఇంబ్యాలెన్స్ కనబడింది. సో ఆ రకంగా నెంబర్ ఆఫ్ క్యాటయాన్స్ యానియాన్స్ యొక్క రేషియో ఐడెంటికల్ కెమికల్ ఫార్ములా కన్నా డిఫర్గా ఉంటే దాన్ని మనం నాన్ స్టాయికోమెట్రిక్ డిఫెక్ట్ అని పిలవాలి. దట్స్ వాట్ వీ కాల్డ్ నాన్ స్టాయికోమెట్రిక్. ఆ రేషియో ఆఫ్ క్యాటయాన్స్ అండ్ యానియాన్స్ కనుక డిఫర్ అయితే. కానీ డిఫెక్ట్ జరిగిన తర్వాత కూడా ఆ రేషియో ఆఫ్ క్యాటయాన్స్ అండ్ యానియాన్స్ ఎగ్జాక్ట్గా ఐడియల్ కెమికల్ ఫార్ములాతో ఈక్వల్గా ఉంటే గనక ఆ డిఫెక్ట్ని మనం ఏమని పిలవాలంటే స్టాయికోమెట్రిక్ డిఫెక్ట్ అని పిలవాలి. Students, are you got it? So this is stoichiometric defect, and these defects may also be called, these defected compounds may also be called Daltonoid compounds. Okay, now let me coming to Scotty defect. Okay, now నేను ఇప్పుడు Scotty defect ని చూపిస్తాను మీకు. Now let us consider NaCl crystal once again here. Let us consider NaCl crystal. Students, keep in mind NaCl crystal we have. Just look at this is NaCl crystal. Okay. Okay, and now this is Na plus Cl minus Na plus Cl minus Na plus Cl minus, and once again Na plus, students. Okay, Cl minus, and here Na plus. Students, we just look at what is going on. Some of the ions are missing. Which ion missing here, sir? Here Na plus ion is missing. Which ion missing here, sir? Here Cl minus ion is missing. So it arises due to, Scotty defect arises due to missing of ions from lattice position. Lattice positions nunchi some of the ions miss avadam valla vacheటువంటి defect ఇది. Okay, but keep in mind, sir, ఒకవేళ కేవలం Na plus ion మాత్రమే మిస్ అయితే, సార్ Na plus ion మాత్రమే మిస్ అయితే పాజిటివ్ అయాన్స్ నెంబర్ తగ్గిపోతుంది, నెగిటివ్ అయాన్స్ నెంబర్ పెరిగిపోతుంది. So we found some electrical imbalance. Okay, no solid exists with electrical imbalance, my dear students. Every solid satisfy electrical neutrality, means the total positive charge obviously equals to total negative charge. Okay, so that's why how many number of cations are missing is exactly equals to the number of anions missing. So in every crystal during Scotty defect, equal number of cations and anions are missing. Equal number of cations and anions are missing for the only purpose to maintain electrical neutrality. Okay, so that's why the number of cations missing is always equals to the number of anions missing, and that's why the Scotty defect maintains, dear students, stoichiometry. Students, are you got it? Because equal number of ions are missing. Students, we know one thing, the best examples of such a crystals which show Scotty defects are NaCl, KCl, CaCl, KBr, AgBr, etc. But students, keep in mind one thing, and this defect arises in crystals having high coordination number. Students, we already know what is radius ratio. What is radius ratio? You know what is radius ratio? Our previous classes, radius of cation by radius of anion. Students, are you remember? Okay, are you remember that table, students? First of all, less than 0.15, coordination number 2, 0.15 to 0.225, coordination number 3. This is row, this is coordination number, this is 0.225 to 0.414. Students, coordination number 4 means what we observe, coordination number increases, students, with increase in radii ratio. Okay, so students, one thing here, this arises in crystals having high coordination number means high radii ratio. High radii ratio possible if and only if these two ions are having almost similar radii. ఆల్మోస్ట్ సిమిలర్ రేడియే ఉన్నప్పుడే కదా ఇది 4 ఇది 4, అప్పుడు రో ఎంత అవుతుంది, మ్యాక్సిమం 1 అవ్వట్లా స్టూడెంట్స్? ఓకేనా? ఇప్పుడు ఫర్ ఎగ్జాంపుల్ రేడియస్ ఆఫ్ క్యాటయాన్ 2 రా, రేడియస్ ఆఫ్ యానియాన్ 8 రా, 2/8 ఎంత అయిందిరా? 0.2 కదా రేడియస్ రేషియో లో. ఓకే, సో హై రేడియస్ రేషియో ఈజ్ పాసిబుల్ ఇఫ్ అండ్ ఓన్లీ ఇఫ్ ద రేడియస్ ఆఫ్ క్యాటయాన్ అండ్ యానియాన్ ఆర్ ఆల్మోస్ట్ సిమిలర్. ఆల్మోస్ట్ సిమిలర్ కింద ఉన్నప్పుడు మాత్రమే ఈ రేడియే రేషియో ఏదైతే ఉందో అది హై కింద కనబడుతుంది, అప్పుడే మనకి హై కోఆర్డినేషన్ నెంబర్ రిజల్ట్ అవుతుంది. అటువంటి క్రిస్టల్స్లో మాత్రమే స్కాటీ డిఫెక్ట్ అరైజ్ అవుతుంది, ఎందుకంటే సైజెస్ ఈక్వల్గా ఉన్నప్పుడు మాత్రమే క్యాటయాన్ మిస్ అయిన వెంటనే యానియాన్ కూడా తన లాటిస్ పొజిషన్స్ నుంచి మిస్ అవ్వగలదు. Students, okay now. And students, we know one thing. This is defect arises due to the completely missing of ions. If ions are completely missing, what about the density, sir? Obviously, density decreases. So, if some of the ions are missing, which create what, sir? Which create holes. So, these holes are further occupied with some of the ions from the respective adjacent positions. Means we found migration of ions. Why not? Migration of ions. Here, this is a hole. Some of the ions are occupied this position. That is nothing but migration of ion. And that migration of ion is responsible for somewhat conduct electricity. Students, are you got it? So these are all we found with respect to our first defect, what we called Scotty defect. Students, and now we have a formula, students, to calculate number of Scotty defects here. What is the formula, sir? We just look at number of Scotty defects in a given crystal lattice. Small n is equal to capital N into e power minus e by 2 kt. Very, very important formula in advanced point of view. What is small n? Number of Scotty defects. What is capital N? Number of ions present in the given crystal lattice, both cations and anions, the sum of ions. What is E, sir? The energy required to create n number of Scotty defects, because we supply some energy by heating or what we call by heating, we apply some energy, and that energy makes a Scotty defect by just erasing what we call vacant positions in the crystal lattice. If we supply some energy, that ions gain that energy and they are escaped from the lattice position. Okay, and what we observe, some of the ions are missing. So Scotty defect arises if and only if we supply some energy. Okay, and that energy required to create n number of Scotty defects, what we call required energy. Okay, now what is K, sir? We know Boltzmann constant. K means we already know in our first year states of matter chapter, Boltzmann constant. Okay, what is its value? I remember 1.36 into 10 power minus 23 joule per Kelvin molecule. Students, I remember. What is T, sir? T means absolute temperature. So if we substitute all the values in a above expression, we are ready to calculate how many number of Scotty defects arises in a given crystal lattice. Very, very important one, students. Okay, students, now after the completion of Scotty defect, now let me coming to Frankel defect. What is Frankel defect, sir? And let me show Frankel defect with the help of diagram. Just look at students, what is going on. Just look at. I'm ready to give a diagram. Let us consider AgCl is a best example to show Frankel defect. Students, just imagine this is Ag plus, this is Cl minus, this is Ag plus, students, and this is Cl minus once again, students, and this is Ag plus, and this is Cl minus, and this is Ag plus, and this is Cl minus, and this is Ag plus. Students, what we found? Some of the anions are missing here. Are you got it? You know one thing, actually anions are large in size compared to cations. Okay, so here anion is missing. So this is Scotty defect? No, this is of course missing, but this is not at all missing. This is just shifting. Shifting of what, sir? Shifting from lattice positions to interstitial position means the ion again reappears in this interstitial position. Keep in mind, students, Cl minus is observed here in this lattice position to create hole once again. Okay, so what is Frankel defect, sir? This is completely opposite to Scotty defect. It arises due to just shifting of ions from lattice positions to interstitial positions, not at all missing. So all ions are present within the crystal lattice, and that's why there is no disturbance for density. Have you got it? Density remains same, because this is not at all missing, just a shifting. Okay, so this arises in what type of compounds, sir? Students, actually this arises in such a compounds in which large difference we found between sizes of cation and anion. large difference. Okay, cation is very small. Okay, it is easily fit into this particular lattice position. But compared to size of cation, the size of anion is very large, very large. So that large anion is unable to fit into this small lattice position. Okay, large anion is not at all ready to fit, and that's why anion itself migrate from these lattice positions to interstitial position, because interstitial position is somewhat having more wide space compared to this lattice position. And that's why shifting of ions is possible if and only if in such a crystal lattices in which a large difference we found in the sizes of cation and anion. Large difference undali. లార్జ్ డిఫరెన్స్ ఎప్పుడు ఉండాలి? ఇందాక కెమిస్ట్రీ మళ్ళీ ఓకేనా, మనం ఇందాక డిస్కస్ చేసిందే. లార్జ్ డిఫరెన్స్ ఉండాలి అంటే రేడియో రేషియో ఈజ్ వెరీ వెరీ స్మాల్. రేడియో రేషియో వెరీ స్మాల్ మీన్స్ కోఆర్డినేషన్ నెంబర్ లో. So opposite to Scotty defect students, opposite to Scotty defect, Frankel defect arises in what type of crystal lattices, sir? Those type of crystal lattices which are having low coordination number, low radial ratio. Okay, and once again some of the ions are enters into interstitial position, the conductivity ability is also increases for that crystal because ions are under movement. So obviously dielectric constant of crystal increases, dielectric constant of crystal increases. Is it clear, Nana? Okay, so this is what we call simply Frankel defect. Students, we have formula to calculate number of Frankel defects also. So what is the formula of number of Frankel defects, sir? Just look at small n is equal to capital N by Ni whole power of, means under root, into e power minus e by 2kt. We already know what is capital E, what is K, what is T in my previous Scotty defect concept. Okay, what about N and Ni, sir? N means number of ions. What about Ni, sir? I represent the number of interstitial positions. Okay, so if you know all these values, we are ready to calculate the number of Frankel defects, and which is a very very important even in maths and advanced point of view, students. And here one neat bit arises in my previous examination papers. We just look at which of the following compounds show both the Scotty and Frankel defects. Keep in mind. Okay, so only one ionic solid is there, which is silver bromide, and which is capable to show both the Scotty defects and as well as Frankel defects. So after the completion of stoichiometric defects, students, now let me coming to a second type of point defects, non-stoichiometric defects. Very very important one. What is non-stoichiometric defect, sir? So what is non-stoichiometric? I think we already understood. Okay, the ratio of cations and anions present in the compound is differ from ideal chemical formula. సో ఐడియల్ కెమికల్ ఫార్ములాలో ఉన్నటువంటి క్యాటియాన్స్ అండ్ యానియాన్స్లో క్యాటియాన్స్ నెంబర్ కానీ యానియాన్స్ నెంబర్ కానీ తక్కువ కానీ ఎక్కువ కానీ ఉంటుంది, ఎగ్జాక్ట్గా ఉండదు. సో ఆ రకంగా స్టాయికోమెట్రీలో ఇంబ్యాలెన్స్ కనబడితే ఆ డిఫెక్ట్ని మనం నాన్ స్టాయికోమెట్రిక్ డిఫెక్ట్ అంటాం. ఈ నాన్ స్టాయికోమెట్రిక్ డిఫెక్ట్నే ఉన్నటువంటి కాంపౌండ్స్ని మనం బెర్తలాయిడ్ కాంపౌండ్స్ అని కూడా పిలుస్తాం. ఇప్పుడు ఇక్కడ నేను మీకు ఆ నాన్ స్టాయికోమెట్రిక్ డిఫెక్ట్స్లో ఫస్ట్ టైప్ని ఇంట్రడ్యూస్ చేస్తున్నాను, అండ్ దట్ ఈస్ నథింగ్ బట్ మెటల్ ఎక్సెస్ డిఫెక్ట్. While we coming to metal excess defect, students, these are actually two types. The one is metal excess defect due to anion vacancies, and the second one is metal excess defect due to interstitial cations. Students, are you understood my word? Metal excess defect means what we found, cations are excess compared to anions. Okay, cations are excess means stoichiometry disturb. Okay, means stoichiometry doesn't follow, and that's why these defects what we call non-stoichiometric defects, my dear students. Students, come on, most important students, very very important in objective point of view. డ్యూ టు anion వేకెన్సీస్. ఎలా సార్ మెటల్ ఎక్సెస్ డిఫెక్ట్ డ్యూ టు anion వేకెన్సీస్? ఇక్కడ వచ్చిన ఎగ్జాంపుల్ తీసుకున్నా గమనించావు నువ్వు? ఎక్సెస్ ఆఫ్ సోడియం ఇన్ NaCl. Excess of sodium in NaCl means what, sir? We just look at, we are consider a perfect NaCl crystal here. Perfect NaCl crystal, students. Keep in mind. Perfect NaCl crystal. Now let me show. This is a perfect NaCl crystal. Say this is Na plus. Say this is Cl minus. Say this is Na plus. Say this is Cl minus. Say this is Na plus. Cl minus. Na plus. Cl minus. This is Na plus. Students, just imagine here Cl minus ion is there. ఉందనుకుందాం ముందు. పర్ఫెక్ట్ సాలిడ్ అనుకుందాం, అది ఎటువంటి డిఫెక్టివ్ లేదు. ఇక్కడ Cl మైనస్ ఉంది. ఇప్పుడు ఏం చేయమంటున్నాడు వీడు? జస్ట్ హీట్ NaCl క్రిస్టల్ ఇన్ ప్రెజెన్స్ ఆఫ్ ఎక్సెస్ ఆఫ్ సోడియం. ఎక్సెస్ ఆఫ్ సోడియంలో హీట్ చేయమంటున్నాడు. ఎప్పుడైతే ఎక్సెస్ ఆఫ్ సోడియంలో హీట్ చేస్తామో సోడియం ఆ హీటింగ్ నుంచి వచ్చేటువంటి ఎనర్జీని అయనైజేషన్ ఎనర్జీ కింద తీసుకుని తన వ్యాలెన్సీ ఎలక్ట్రాన్ని లూజ్ అవుతుంది. జస్ట్ లుక్ ఎట్. మీన్స్ సోడియం ఈజ్ కన్వర్టెడ్ టు Na plus. Once Na plus ion is there, Cl minus ion from this position, students, ikkada unna Cl minus ion, so it leaves this position and go and combine with Na plus. ikkada unna Cl minus, so ikkada nunchi వెళ్ళిన Cl minus ఆ Na plus తో కలిసి it form NaCl. It form NaCl. So a anion vacancy created here. Not only here. Here Cl minus is there. Here Cl minus is there. So the number of Na plus ions increases here. More number of Cl minus ions leave their positions and combines with the Na plus ion here. So we found more number of anion vacancies. More number of anion vacancies, students. Anion vacancy means cations are there, but some of the anions are missing. Ratio of cations to anion missing. Metal ions are appears to be excess. Okay, and that's why this defect what we call metal excess defect. And why it is arises, sir? Because some of the anions are missing to create anion vacancies. Students, have you got it? Very, very important one. But students, keep in mind, if some of the anions are missing, electrical neutrality disturbed. Okay? To maintain electrical neutrality, these anion vacancies are again occupied with these unpaired electrons. Just look at unpaired electrons. Just to maintain electrical neutrality. Okay, and these anion vacancies which are occupied with unpaired electron, and these sites what we call F centers. Very, very important in IP and objective point of view. What are F centers, sir? F centers are nothing but the anion vacancies which are occupied with unpaired electron. Why unpaired electron coming to here? To maintain electrical neutrality. Keep in mind, students. Okay, students, so whenever we are just heating sodium in NaCl crystal, this electron reaches to higher energy states. It is not stable there. Once again it comes to ground state by emitting some energy radiations, and these energy radiations belongs to which color zone in VIBGYOR, and that crystal appears in that color. Why F centers impart color to the crystals, sir? F centers impart, students, color to crystals. Why, sir? And this is the reason behind. Because these electrons are responsible to give color. You know what is F in Latin? Farbacenter. Farbacenter means color. Sodium heated in NaCl, yellow color. Lithium heated in LaCl, pink color. Potassium heated in KCl, violet color. So the color behind all these crystals are mainly due to which centers, are F centers. Okay, so this defect arises in such a manner some of the anions are leave their positions to create vacancies. Okay, and that's why due to anion vacancies some of the metal ions appears to be excess, stoichiometry disturb. That defect what we call metal excess defect. The second metal excess defect is due to interstitial cations. Interstitial cations into enti sir, let me explain. And this defect arises when extra metal ion present at interstitial site. Keep in mind, extra metal ion is present at interstitial site. Okay, how extra metal ion present at interstitial sites, sir? Give me an idea. Okay, now let me give an example. Zinc oxide. Students, we know one thing. This is actually Zn plus 2 students, O minus 2, and this is Zn plus 2 students, and this is O minus 2, and this is Zn plus 2, and this is O minus 2. Students, okay? Perfect tester. But whenever zinc oxide is on heating, students, what happens, sir? Zinc oxide upon heating, students, keep in mind, zinc oxide upon heating Zn plus 2 plus O minus 2. O minus 2 further turns to of oxygen gas and along with 2 electrons. Oxygen gas escapes. Being a gas, it is escape. By just leaving only metal Zn plus 2 ions. And these metal Zn plus 2 ions occupies what, sir? These metal Zn plus 2 ions occupies interstitial position. But electrical neutrality doesn't maintain. The positive ions are overcome, positive ions are more. To maintain electrical neutrality, here the rest of electrons, they just go into adjacent interstitial positions, students, to maintain electrical neutrality. What about oxygen, sir? Oxygen is escape. Okay, means some of the cations are present in excess number in interstitial position. Okay, sir, why zinc oxide upon heating it turns to yellow color, sir? And once again, the reason behind this is the excitement of these electrons to higher energy states, and these electrons are responsible to give zinc oxide upon heating gives yellow color. Students, we know one thing. Whenever this yellow color zinc oxide upon cooling, it becomes once again colorless. It becomes once again colorless. You know why? Because upon cooling, what happens? The atmospheric oxygen is again converts to O minus 2 and again reaches its original position, and that's why there is no chance to exhibit color. Students, is it clear? And this is what defects are, and is simply called interstitial cations defect, because cations number is excess, and that defect what we call metal excess defect. అందువల్ల జింక్ ఆక్సైడ్ ఫార్ములా కూడా చూడండి, ఫర్దర్గా ఏమైందో Zn1 + x ఓటా, అంటే ఆక్సిజన్స్ యొక్క నెంబర్ కన్నా హీట్ చేసినప్పుడు జింక్ అయాన్స్ యొక్క నెంబరే ఎక్కువ ఉంటుంది. ఇది 1 మోల్ రా, కానీ ఇది 1 మోల్ కాదు, 1 + x means Zn plus 2 ions are excess, and this defect what we call due to interstitial cations metal excess defect. Okay, students, and this is some part of defects in crystals, and the rest of part we follow my next video, students.